right, we have another example of a collision. So we want to hit this pin at a glancing blow, meaning right on the edge. So it sends the pin, this is our pin, it sends that off into the right, which means the ball itself is going to have to go off to the left in terms of conservation of momentum. So we are assuming this ball is traveling 12 meters per second initially, so right before it hits the pin. It's telling us the ball, so mass of the ball is 5 times the mass of the pin. It tells us the pin goes off with a speed of 3.5 meters per second at this 80 degrees, which is shown in the picture. What is the velocity? So magnitude and direction. We're trying to find the theta that's in this picture, and then how fast the ball will be traveling right after the collision. So since this is a collision, momentum is conserved. When we write out momentum, mass 1, V1 initial, plus mass 2, V2 initial, we need to account for both objects, object 1 and object 2, in this collision. And I wrote it backwards again, but luckily the order of addition doesn't matter. Actually, I'll put it in when I set it up in the opposite order, so let me fix that. V1 final plus M2 V2 final. So we need to decide which object we're calling object 1 and which object we're calling object 2. It doesn't really matter. What matters is that we are accounting for the momentum, so mass times velocity. So if we go ahead and say the ball is object 1, that will make the pin object 2. So this relationship between their masses, we could say mass of object 1, the ball, is equal to 5 times mass of object 2, the pin. Now, because motion, as soon as the ball hits the pin, we have some x direction motion and y direction motion. We do need to look at conservation of momentum in the x direction, independent of the y direction. So we're using this equation, and we're going to use x components of velocities all the way through. And then similarly, we'll do so again with y components. So in the x direction, I'm going to just put in m1 for the ball because I don't know its mass. But I do know it is not moving in the x direction at all initially. I'm going to put in m2 for the pin. But again, it's not moving at all initially. So all of the momentum in the x direction specifically is 0. And you could totally just write 0 in the first place if you recognize that. After the collision, the ball is moving. We do not know its final x velocity. We expect it to be to the left, but we'll let the equation show that to us. The pin is moving to the right, and we can determine its velocity in the x direction. All right, so in place of m1, I'm going to put 5m2, so that I have m2 in here, and that will cancel. So having a relationship between the mass of the two objects, I can still solve the problem. So let's see, we're going to solve 5v1x final is going to be equal to negative v2x final. So let's figure out v2x final. That is the final velocity of the pin. We know it is traveling at 3.5 meters per second. I'm going to draw this down below and at a slightly different angle just to see it better. So this angle in here, they've told us is 80 degrees. So Vx of the pin is going to be 3.5 meters per second times the sine of 80 degrees, because we're opposite that 80 degrees. You could also, if you'd like, do 10 degrees down here, that's fine, and 3.5 cosine 10 is the same thing. So 3.5 sine of 80 degrees. This gives us ball 1's x component of velocity finally. The negative sign means to the left, because the ball was headed to the right. So the equation gives us that. Plugging numbers in, I'm getting 0.6894 meters per second. So not very fast. To the left. To finish this velocity, so the ball, if I was to draw V of the ball that we're looking for over here on the left, we have just calculated this x side to be to the left, which I can see in my picture, 0.6894 meters per second. So we need to get the Vy final in order to be able to find the magnitude and this angle that the vector is pointing at. All right, conservation of momentum in the y direction. So same equation, but instead of x's, we're going to have y components. So mass 1 is the ball. Mass 1, V1 initial, in the y direction, which is the 12 meters per second, plus a mass 2, but it's not moving at all initially. So it doesn't have x or y components of velocity initially. That's going to equal mass 1 times its y component of velocity plus mass 2 times its y component of velocity. So let's go ahead and put in what we know as well as the relationship between the masses. Or we can just put the relationship between the masses. I don't know. Let's see. 5 mass 2 times the 12 meters per second that the ball is traveling in the y direction. So this is the total momentum. So 5m2 because the ball is 5 times the mass of the pin. The 12 because 12 meters per second is the speed. That has to equal, the ball is still 5 times the mass of the pin. We're looking for this final y component of velocity of the ball. That's going to be in our picture below, that vertical side. Mass 2 is the pin. We don't know the value, but that's okay. In the y direction for the pin, we know the speed is 3.5. The y component is adjacent to that, so we will have 3.5 cosine of 80 degrees. So this is the final y component of the velocity of the pin. And again, you could have 3.5 sine 10. That works as well. Now that we've put the relationship of the masses in there, the m2, the actual value of the pin's mass, cancels. So we end up with 60 on the left side, 5 V1 final plus 3.5 cosine 80. So we can solve for V1 final here. I'm getting 11.878. So I'm going to replace that in my picture far on the left. The magnitude, the speed of the ball is simply going to be the Pythagorean theorem, which is essentially going to give us 12. But I'll show you what I get. 6, 8 squared. So 11.898. So the ball is still traveling essentially 12 meters per second. So to 2 sig figs, it's still 12. It, of course, is not exactly 12 anymore. It's slowed down a tiny bit because some of its momentum went to the pin. The angle, we can say the tangent of the angle theta they've drawn in the picture and asked for would be 0.6894 over 11.878. So when I take the inverse tangent of that, I'm getting 3.3 degrees. So a very small angle. Now I'm leaving it as the 3.3 because they've drawn theta in the picture and asked for what theta is. So I'm saying theta, the angle they've drawn in the picture, is 3.3 degrees. So anything that is a collision or some sort of explosion of sorts, we can always jump to conservation of momentum. The nice thing is momentum is conserved in any collision regardless of the type of collision. It doesn't matter if the objects stick together or not. Momentum will be conserved in a collision simply because the forces are internal to the system, those forces that change the motion. So momentum is always my go-to when I see a collision occur or an explosion of sorts. Beyond that, I can look at other concepts. So we're going to do a couple more examples that will require us to use more than conservation of momentum. So we'll look at that next.